In this video, we're going to look at what happens when you want to remove more than one electron. So previously, we saw the ionization energies for if you're removing a single electron. These are the first ionization energies. How hard is it to remove the first electron that you remove? But you can have ions that have more than one electron removed. Magnesium becomes magnesium 2+ and 2 electrons. Well, how does that start affecting things? Once you've removed one electron, how does removing the second electron fare? Really, what we have here is a two-step process. Magnesium becomes magnesium plus and 1 electron, and then magnesium plus becomes magnesium 2+ and a second electron. You have to remove electrons stepwise. Here in our table 8.5 from the book, we can find a series of ionization energies for the third through the 11th element. Let's look at lithium and sodium. Both of these are NS1 elements, so 2s1 and 3s1 for sodium. What we notice, if we look at the energy, the first ionization energy is less for sodium. It's easier to remove an electron from sodium than lithium. And these are in megajoules per mole, so that's 20 kilojoules difference between the two. Not huge, but noticeable, and this trend continues. As you go down the periodic table, you will have less and less energy to remove an electron. Those orbitals are just further out. Those electrons aren't held as tightly because they're further from the nucleus, and so it's easier to remove them. As we move to the right on lithium, what we find is the energy to remove the second electron. So not both. 7.3 megajoules per mole is the energy for the second electron's removal. It's 7.3 megajoules instead of 0.5. Approximately 14 times greater energy. This is a massive increase in energy. What's happened is, lithium, 1s, 2s had its 3 electrons, going to lithium plus, we just have the 2 electrons. The first ionization energy was targeting a 2s orbital, but the second ionization energy has to remove from a 1s. The Z effective for lithium is +1, but for the 1s orbitals, that's a +3 Z effective. It sees all 3 protons. It is significantly harder to remove because it is more attracted than the electron in the 2s orbital. And additionally, by being a cation already, there's just extra positive charge. With that one less electron, your ion has gotten smaller, so the remaining electrons are even closer to the positives. As a result, they are significantly stronger attached. Like we say, 14 times more energy to remove the second electron. And if you want to remove the third, it's also more, but not quite as much more. It's not 14 times the last one. If I'm at lithium 2+ with a single electron in the 1s, and I want to remove it, it sees the 3 pluses, it's shrunk and gotten a lot closer, but it didn't have the drop from the 2 shell to the 1 shell, like we did for the second ionization energy. Ionization energy 2 and ionization energy 3 are both already in the 1 shell, so the only increase we're seeing going from the second ionization to the third is the contraction as the orbitals get closer as electrons are removed. Well, these two effects compound with each other. If we look at beryllium, going from beryllium to beryllium plus and then beryllium 2+, but removing the second electron from beryllium is barely twice the energy. In fact, it's not even twice the energy. If I have beryllium, 1s, 2s, 1, 2, 3, 4, And I go to beryllium plus. I've still got my 1s, I've still got my 2s. I've removed 1 electron from the 2s, and it took 0.9 megajoules. Well, if I do it again and I remove the next one, it's still coming from the 2s. When I get to beryllium 2 plus, I have 1s, 2s. I haven't taken an electron from my core yet. I was still removing from valence. And while it did take more work, it wasn't significantly more work. As soon as I tried to take a third electron, I go from 1.7 to 14.8 megajoules. Again, a massive increase, but that was because it would have required removing a core electron. I would have to drop down to a higher Z effective influenced orbital. As a result, it massively increases our energy. Taking valence electrons is easy. Taking core electrons is very difficult. So we see repeatedly here, as you go from your valence to your core, the energy jump is massive. For many of these elements, you have to remove a lot of electrons before you could get to the core. Taking neon down to +8 is very difficult. It takes an enormous amount of accumulated energy to do it. Doing this in the lab would be very difficult. However, the first ionizations aren't really that bad, and they don't go up by a significant amount. So removing electrons from the valence shell, while it does take more energy for each subsequent electron removed, because the cation is a little bit more positive, it pulls all the electrons in a little closer. As long as you're taking from the valence, they're more reasonable energies. If you're trying to take from a core, it is a massive increase in energy. In the same way that we can remove electrons, our last thought process then is, what about the anions? What about adding electrons? I have fluorine, and I can add an electron and make F-. We have to put energy in to knock an electron off of an atom. But if I have fluorine here, 1s, 2s, 2p, and somewhere up above is the free line. 1, 2, 3, 4, 5, 6, 7, 8, 9. And we have some electron just floating in space, and then it falls and bonds to our atom. Well, that orbital is lower in energy than floating free. They'll have two opposite charged magnets rolled near each other, they'll pull together. That electron will attach to our fluorine. This is how we make anions. Well, if that electron had to go down in energy to get to the orbital, it must give off that energy, usually as a photon. What we actually see is, the energy required is negative 328 kilojoules. These are in kilojoules. We give off energy. Fluorine, picking up an electron, gives away 328 kilojoules per mole. If we look at this chart, basically every element, except for nitrogen, which I'll talk about in a second, gives off energy. It is favorable. Even sodium, even potassium, elements we expect to be cations, they actually give away energy when you make them an anion. Because the orbitals are always closer to the nucleus than a free electron is, that electron will always give off a little energy when it comes in to take a spot in the orbitals. So why don't we see a lot of sodium minuses and potassium minus? Well, because as soon as it bumps into anything else, it would rather transfer its electron to the thing that has a deeper energy well. Na minus and F is just going to immediately become an Na and an F minus. The elements that want the electrons more will definitely pick them up. But that's if we had one that already had a minus charge. If we actually try to compare things for a moment, think about a reaction of sodium plus fluorine. This would make 2 sodium fluoride, which is really an Na plus and an F minus. We have to remove the electron from one element and put it on the other. Curiously enough, if we think about the energies for a second, to ionize sodium takes 500 kilojoules. The energy you get back putting them on fluorine is only 328. The energy of making the ion isn't actually favorable. As we'll discuss in Chapter 9, there's extra components that become involved, but just transferring the electron itself actually isn't favorable. Atoms would rather stay neutral or gain electrons than give them away when we make reactions happen. So what's going on with the odd situation out? What's going on with nitrogen? This actually has everything to do with the ionization energy between nitrogen and oxygen. With nitrogen, we had the 2s and the 2p, and with N minus, which electronically looks a lot like oxygen, 2s and 2p, there's 6 valence electrons. Remember we said oxygen was a little bit easier to remove that electron from because you had to pair the electrons. Well, when it's nitrogen gaining an electron and pairing, you don't even get the extra Z effective. So you're just adding a bunch of extra energy requirement to pair without any of the benefit of the extra protons. As a result, it actually pushes it up just a little past the break-free point. To pair the electron on nitrogen is difficult enough that the electron actually more or less prefers to float free. You don't notice that for phosphorus and arsenic and like because once the orbital is bigger, it's easier to pair. And so getting a negative charge near a positive charge ends up being more beneficial than getting those two negatives near each other. The 2p orbital nitrogen is just too small. The pairing energy is too great, despite getting a new negative near the positives of the nucleus. And so a few extra trends that we tend to see. Ionization energies, when you're going beyond the first ionization energy, continue to follow the same trends we saw with the first ionization energy. They just have a very large jump when you get to core electrons. But as you can see, removing that first core electron gets harder and harder as we go across the periodic table. But as we go down the periodic table, it gets a little bit easier. Lithium to sodium here. We can see that even the second or third ionization is easier off of sodium than it is off of lithium. Going down a column, it is less energy. Going to the right on a row, it is more energy.